Okay, so good afternoon, everybody. It's a great pleasure to introduce the next speaker, Dr. Mainak Ghosh from ISI Bangalore, who completed his PhD from TIFR last year. And he's going to be talking about zero-sum problems for metacyclic groups.
Thank you for the introduction and thank you to the organizers for this opportunity. I will be talking on the zero sum problem, and we will begin with a simple pigeonhole principle exercise that many of you might have seen. So let's say I have a sequence of n integers, then can we always find a non-empty subsequence of this, whose sum will be divisible by n? So as all of you might know, the answer is yes. And how do we prove it? We just take this progressive sums of starting from A1, and we call them, if we call them B case, then we'll have n minus 1 many these sums, and we have exactly n many residue classes modulo n. So therefore, by pigeonhole principle, two of them must be lie in the same residue class, right? And if it is Bk and Bl, then this sum up to k and up to L are both same modulo n. So their difference will now be divisible by n. So if we take the sequence in between, that will be a subsequence of S whose sum is divisible by n, right? So this is a fairly simple exercise, but this shows us a property about the group Z mod nz. So to explain that, we will first define the Davenport's constant. Given a group G, we define a sequence of elements of G to be some tuple G1 up to Gn, where every element is actually an element of G, and these may repeat. And we call such a sequence a zero-sum sequence if the elements add up to 0. But we don't need to add them like G1 plus G2 up to Gn. We can permute and add them also. So in case it's an abelian group, the permutation doesn't really matter. But if we move to non-abelian group, then the permutation might come into picture. And we'll call it zero-sum free if there is no subsequence of it which adds up to 0 at all. And Davenport's constant is defined to be the minimum number dg, such that if you have a dg length sequence, then it is guaranteed to have some subsequence which adds up to 0. Again, in some order, it doesn't need to be in the increasing order only. And yeah, so that's the Davenport's constant. And there's an alternate way of defining it as well. We can instead take the length of the maxima, the highest zero-sum free sequence, and then I add 1 to it. That will also be a Davenport's. That will also be the same as Davenport's constant.
The group is not complicated.
No, my group need not be abelian.
You're writing.
Yeah, it's the notation is a bit confusing. Sorry about that. And what we saw is that the Davenport's constant of Zn is actually less than equal to n, right? But on the other hand, if we just take n minus 1 many copies of 1, then there is no subsequence of it which adds up to 0 in Zn. So therefore, we will get that d of Zn is equal to n. And using the same argument, we can get a trivial bound on Davenport's constant of any finite group G, which is the order of the group, because we'll again take the progressive sums, and if any two of them are the same, then the difference will give me a subsequence which adds up to 0. Now we move up to higher rank abelian groups, and we know that structure theorem will tell us that there is a unique way to represent this group G as direct sum of Z mod nkz, where this n1 divides n2 divides n3 up to nk. Now for such a group, we can find a very easy bound for Davenport's constant. So what is that? So let's say ei to let's say I take e1 to be the 1 and then the rest of them as 0. E2 is that it is 0, 1 and the rest as 0. And similarly, ek is everything is 0 except the last one. And I take n1 minus 1 copies of this, n2 minus 1 copies of this, and up to nk minus 1 copies of this. So this is my sequence. And the sequence length is summation of ni minus 1. And clearly, this sequence does not have any zero-sum subsequence. Why is that? Because if I add up any subsequence of it, I will get something like this, right? A1, A2, up to AK, where every AI is bounded strictly above by ni, and below it's greater than equal to 0. But at least one of them has to be greater than 0, because otherwise we are not adding anything at all. So therefore, this sum will not vanish in that group, right? So therefore, we see that this is a zero sum. This is a sequence which is zero sum free. So therefore, the diamond force constant must be at least one more than this. So that's how we get the bound, and we call this constant mg, and we get that dg is greater than equal to mg for all finite abelian groups. Right. Now, Ulson showed that if your group is actually rank 2, then this dg will actually be equal to mg. And he has also shown that if your group is a p group, that is some z mod p power ai, where all the primes are the same, then dg is again equal to mg. And he had conjectured that dg will be equal to mg for all finite abelian groups. However, unfortunately for us, the Ulson's conjecture does not hold. So we saw that for rank 1 and rank 2, it holds. For rank 3, it is unknown whether all rank 3 finite abelian groups it will hold or not. But for rank 4, there are infinitely many counter examples to the Ulson's conjecture. So one such family would be this: if you take a odd number, which is at least 3, and then add 3 copies of z mod n and 1 copy of z mod 2n, then dg will be strictly greater than mg. In fact, Bhomik and collaborators has described some algorithm to, if your group is of this form, then there is an algorithm to show whether Ulson's conjecture will hold here or not. And actually, let's say you take any number m, you will be able to produce some finite abelian group for which the difference between dg and mg is at least m. So we see that for abelian groups also, we don't really know how to compute the Davenport's constant for all of them. And so some people have also moved over to non-abelian groups and tried to compute these constants for non-abelian groups as well. So one important such paper was Bass's paper, where he computed the Davenport's constant and another constant called the Gauss constant, which we are not going to discuss because of lack of time, for several classes of non-abelian groups. One of them is the dihedral group D2n. Another one is the dicyclic group Q4n, which is quite similar. X power n is again y square, but instead of x power n being 1, we just have x power 2n is 1. And in fact, if you go take qn and go modulo 1 comma y, then it will be actually D2n. And also we have the metacyclic group ZA semi-direct ZB, which we describe as x power b and y power a is equal to 1, and yx is equal to x power g times y. And we will impose a further condition that the order of g modulo b is a. This ensures that the map of za into this automorphism group of zb, I want this map to be ejective, because otherwise this will just break into a product of a cyclic and the metacyclic group, and I don't want that. So Bass showed that the Davenport's constant of D2n is n plus 1. The Davenport's constant of Q4n is 2n plus 1. And if you take B to be a prime, then Bass showed that the Davenport's constant of nqg is just n plus q minus 1. And note that since we are taking the order of this order of g to be n modulo q, then n has to divide q minus 1, because zq star is actually zq minus 1. Right? Okay. And then he conjectured that for a general metacyclic group, as long as this injection holds, that the Davenport's constant would be a plus b minus 1. And he also predicted something for Gauss constant, which we are not getting into. And so notice one thing, that if we take this ZA semi-direct ZB, if I take x and a minus 1 copies of x and b minus 1 copies of y, then there is no way to get a zero-sum subsequence out of it. So therefore, I already get that d of zabg is greater than equal to a plus b minus 1. So the real challenge is proving the other side, that if you have a sequence of this length, you will always be able to find a zero-sum subsequence. And this conjecture, there has been some progress. So for example, Q and Lee showed that if you take a to be prime instead, then and it is smaller than all the prime divisors of n, then we know what is the Davenport constant is again p plus n minus 1. And Han and Zhang has showed that if A divides B, then also Basse's conjecture will hold for the Davenport constant. Okay. Now let's talk about the kth Davenport constant. It was defined by Holter Koch, and he defined it as you define this dkg to be the smallest number such that if you have a sequence of this length, you will be able to extract k many disjoint non-empty sequences, all of which are zero sum out of it. So if k is equal to 1, then it's just that is just the Davenport's constant. But for higher k's, it's a greater numbers, of course. And one trivial bound for the kth Davenport's constant that we can find is k times dkg. Why is that? If I have a sequence of length k times dkg, I can divide it into k many length sequences of each of length dg, and from each of these, by the definition of Davenport's constant, I will get some zero sum sequence, and then they are all disjoint and they are all zero sum. So that gives me k many zero sum sequences anyway. So that acts as a bound for dkg. But we can do better, which we will come to later. And what he showed is that dk of Zn is kn. Also that if you write G in the earlier form as a finite abelian group, then dg will be greater than or equal to mg plus k minus 1 times the highest number. That is also easy to show. You take again ni minus 1 many copies of ei's for all I less than l, and you take knl knl minus 1 many copies of el. So that will be a sequence which will not have k many zero sum sequences, zero sum subsequences. And yeah, and what he showed also that if you take a rank 2 group, then it will actually be equality, and you will say that dk of za dx sum zab will be kab plus a minus 1. Okay. And the two constants which I said I would define. So now let's take a finite group whose Davenport's constant is d. And so since its Davenport's constant is d, I know that if I take a d length sequence, then I will be able to find some zero sum subsequence. But my question is, how large does it have to be? So that is the what fg is. Fg is that if you take d length sequence, then you can find a zero sum subsequence whose length is at most fg. So it could be as high as dg, but not more than that. But it could potentially be smaller. That's all. And the second is, if we take a zero sum sequence, then let's say I have a zero sum sequence to begin with s, which already adds up to 0. I want to say that Eg is the smallest number such that we will always be able to find a zero sum subsequence whose length is at most L. Okay. And alternately, this Eg we can also define as the length of the longest minimal zero sum sequence. But by minimal, I mean that it's a zero sum sequence which does not have a proper sequence which also adds up to 0. Okay. So first of all, we will get some simple inequalities for this d, e, and f. We will get that dg is greater than or equal to eg is greater than or equal to fg is greater than or equal to the maximum of the order for any finite group. And secondly, if you take a finite abelian group, then d, e, and f are the same. Why is that? So so let's say we take some dg length sequence. Now, by the definition of the Davenport's constant, we will find some zero sum subsequence of it, and then by the definition of eg, it will have a further subsequence of length at most eg, which also adds up to 0, which will show us that Eg is greater than or equal to Fg, right? And the other two inequalities are quite simple. So let's say I have this order of H is equal to n. Then if I take a sequence, no matter how long, which only consists of H, then the only way to extract a zero sum subsequence of it is to take at least an n side sequence, right? Because you just have copies of H, so it will be just n times H is 0. So therefore, f will be greater than or equal to maximum of the order, and the dg is greater than or equal to eg is also fairly simple to see. And on the other hand, if you have a finite abelian group, and you take a maximum zero sum free sequence, and we can do it up to a length of dh minus 1. So with that, I just add the elements and I add the negative of it to the sequence. Now it will be fairly simple to see that this adds up to 0, and there is no proper this does not have a proper subsequence which adds up to 0, which will show us that fg is equal to dg, fg is greater than equal to dg, and from the reverse inequalities we will get that d equal to e equal to f in case of finite abelian groups. Okay. Now, so these are like some of the basic properties of E and F, and we saw that these actually coincide with the Davenport's constant in case of finite abelian groups. So let's move over to non-abelian groups and see what happens. So first case we will consider is again the same thing as BAS, dihedral and dicyclic groups. There what we get is that F and E of D2n is both 1 minus it both 1 less than the Davenport's constant. And similarly for Q4n also, F and E are both equal to 1 less than the Davenport's constant. And how do we show it? First of all, so we know that the E and F are both bounded between the Davenport's constant and maximum of the order, and the maximal order being n and the Davenport's constant being n plus 1, they lie between n plus 1 and n. So the only thing we need to show is that Eg is equal to n, but it can only be n or n plus 1. So if it is not n, then it's n plus 1, in which case I find n plus 1 length minimum zero sum sequence. Now since it's minimum, if I delete the first term, then we will get a sequence. So let's say this is the sequence and I delete the first term, then we get a sequence which does not have any zero sum subsequence, right? Because if that had a zero sum subsequence, then then this would not be minimal. So those sequences are called extremal zero sum free sequences because these are of the length dg minus 1. Now we know that the point is that there was a paper by Martinez and Ribas which characterized all extremal zero sum free sequences for D2n as well as Q4n actually. And this basically gives us how all these sequences will look like. I mean, this is for n greater than 3, but for n equal to 3 also there are only 1 or 2 types of. So it's easy to account for those cases. And now what we do is we show that if there is a sequence like this and if we add any element to it, then it cannot be a minimal zero sum sequence because it will have a subsequence which adds up, it will have a proper subsequence which adds up to 0. S is the, sorry, small is just any number. T is something which is co-prime to n, but there is no restriction on S. It could be any power, like starting from 0 up to I guess n. Yeah, 0. Yes, you can take any reflection, and the others are some rotation which is co-prime to n. And so therefore we will get a contradiction because we see that from this, with this extremal sequence, if we add any element, then it cannot be minimal in terms of being a zero sum sequence, and that will give us a contradiction, and therefore Eg will actually be equal to n, and then we are done. And the same argument works for Q4n also, because there also I want to prove that this order is again dg minus 1, and Martinez Rivas has also characterized all extremal zero sum free sequences for them as well, which is all, I mean, of a very similar form. So these two cases are quite simple because, and this happened because our E and if both turned out to be exactly 1 less than dg. And now we will go, we'll talk about metacyclic groups, but before that I would state two potential uses of this constant fg. One would be bounding this k Davenport's constant. So we know that dkg is less than or equal to k times dg. Yeah, k times dg, but we can show that it is actually less than or equal to dg plus k minus 1 times fg. So the way we do it is take some sequence of this length and keep taking out sequences, zero sum sequences whose length is capped by fg. We can do that unless we have dg minus 1 many elements left, and we can see that we will get at least k many sequences, and therefore we get done. And if we have a this allows us to show that the dk of d2n is kn plus 1 and dk of q4n is 2kn plus 1. Why? Because this proposition will give us these bounds kn plus 1 and we take this sequence which consists of kn minus 1 many copies of x and 1 copy of y. From this we cannot extract k many zero sum sequences. So that is easy to see because you cannot involve the y at all, and from kn minus 1 many copies of x you can get at most k minus 1 zero sum sequences. And for Q4n also similar proof will work. And now let's say you have a short exact sequence like this, where G is a normal subgroup of H is a normal subgroup of G and K is its quotient. And one trivial bound for DG now is that it is less than or equal to DH times DK. But instead we can say that it is actually less than or equal to DK plus DH minus 1 times FK. Why? Because I'll describe it in 1 second. And if the equality holds in 1, then F of G will actually be bounded by the product of the F of the other two groups. And how do we do it? Again, we take a sequence of this length and we look at its image inside of K. Now we can take zero sum sequences phi s1, phi s2 up to phi st, which are all of them will be bounded, length will be bounded by fk because we are looking at the sequences in K. And since these sequences add up to 0 inside K, they will be in the corresponding elements in S, they will add up to something in the kernel, which is H. So I will get dh many elements in H. So some subsequence of it will add up to 0, right? So since I am getting dh many elements of inside H, since I'm getting dh many elements here by taking these sequences, I will get some subsequence of them will add up to 0 because that's the definition of the Davenport's constant, and therefore we will get a zero sum subsequence of this original sequence, which proves that it is less than or equal to dg is less than or equal to this number, and correspondingly we will also get the bound on F by the same argument. Now for metacyclic groups, we show that F of this Zp semidirect Zq will be Q if P and Q are both primes. And I'm not going to discuss the proof at all. Yeah, and using this result, we can show that D of the Davenport's constant of P semidirect Zp semidirect Zn is going to be always P plus n minus 1, and F is going to be n. And the way to do it is quite simple. You take this Zp semidirect Zn, and then you find some prime dividing Q such that so this G we have is not congruent to 1 mod n, right? So then we can and we know that the order of G is P mod n. Then we can show using primitive root that there will be some Q dividing n such that G is not congruent to 1 mod Q. And therefore we show that, therefore we see that if we take the subgroup generated by x power q, then the quotient would be Zp semidirect Zq and not direct sum. And the subgroup will be isomorphic to Z mod n by q z. And then the calculation earlier shows us that the upper bound for dg is P plus n minus 1, and the lower bound you already know. So that gives us that dg is equal to P plus n minus 1. And then the same and then the earlier proposition will also tell us that Fg is equal to n. And now the kth Davenport's constant this result will immediately imply what the kth Davenport's constant is, because we'll get the upper bound and the lower bound is taken gotten by taking kn minus 1 many copies of x and p minus 1 many copies of y. And this is, let's ignore that for now. And for general metacyclic groups, our conjecture is that F of Zm semidirect Zn should be n, as long as this injection of Zm inside automorphism group of Zn holds. And the particular case we were interested in is the holomorph of a group Zq. And so that is just automorphism group of Zq acting on Zq as automorphisms. And note that automorphism groups of Zq is just isomorphic to Zq minus 1. So this does form into a metacyclic group. And what we had been able to prove is that this holomorph, the F of holomorph of Zq is bounded above by Q plus half of Q minus 3. But we haven't been able to come down to Q. And just for reference, the Davenport's constant for holomorph of Zq is 2q minus 2, and I want to prove that F is actually equal to Q, but we have been able to prove that it is less than or equal to Q plus Q minus 3 by 2. So it's like we proved that it is in the lower half of where we want it to be. And in fact, we showed that E of holomorph of ZQ is less than equal to Q plus Q minus 3 by 2. As we showed that if you take a sequence of, if you take a zero sum subsequence of holomorph of ZQ, which is of length Q plus, which is of higher length than this, then we will be able to find a proper subsequence which also adds up to 0, which would prove this bound on E. So I think I'm already out of time. So these are some of the references. And thank you for your attention.
So we have time for some questions. Yeah.
I'm not so conversant with these questions, but you have basically you have considered non-abelian groups which are simple modification, deformation, yeah, which are easily derived from cyclic groups, right? DA12s and others. What happens? Is it interesting to consider, say, a sporadic group?
What group?
A sporadic group?
Um,
say the monster. What is DG for a monster?
No, I actually just considered metacyclic groups.
Okay.
Okay. Next. For a general non-abelian group, we don't have a upper bound.
But just to, I mean, Sinu is going too far perhaps, but maybe if you just take other semi-direct products of abelian groups, does it get much harder or can you still employ similar techniques?
We can try to use this the technique of yeah, we can try to use this technique, but I'm not sure if it will work. That trying to find a quotient of
Right.
appropriate quotient. So as long as this, so the point is, as long as this Fk is significantly smaller than dk, then there is a hope for getting good results out of it, out of this bound, which is what happens in case of Zp semidirect Zq, because it's instead of p plus q minus 1, it just turns out to be q. But for example, if the quotient is abelian, then we don't get anything out, almost anything out of it, because then Fk and dk are the same, and this is the same bound as dk times dh.
Yeah, but this is also not assuming semi-direct product. It's an extension.
No, yeah, this is for any extension.
Any more questions? Well, if there are no more questions, let's thank the speaker for this.